This week in Math for Elementary School Teachers, we'll be working with measurement. And that's Chapter 11, Section 1. I'm having some issues with the publisher, and so I can't get in and make a new reading assignment. So we're going to do a little bit different this week. So please take a look at your reading assignment. You're going to do a brief outline based on what you read in the section. And in this assignment, I make a note that there are 5 different main topics in the section, and then I want you to make a note of at least 2 points from each of those sections. And looks my internet's a bit slow today. Otherwise, it's just activities this week with a little bit of homework at the end. And activities focus on doing the Metric Olympics at the end of the week. And there's another video about the Metric Olympics. So maybe that'll load in a little bit. For now, let's do a little bit of work. So the first topic in the book is non-standard units of measure, and often we will make up our own measurement systems, and we've done that historically, and we do that every day probably. When I look at some height, I kind of gauge it. Is that as tall as me? Is that person as tall as me? Are they shorter than me? So I'm using myself as a measuring unit for a comparison. Sometimes I'll use my hand to measure something, or my forearm, or maybe I'll walk something out in feet. For example, when I'm playing around with little kids with soccer, I'll often use my feet to measure some distance for them to stay apart. Um, so we make up units all the time. Other times I'm sketching something out and I don't have a ruler nearby. So, on the edge of a piece of paper, I'll kind of make my own ruler. And one easy way to do that is to just, fold the paper in half and then fold it in half again on each of those sides. And it's pretty easy to fold something in half, so then you can get these nice equidistant measurements by folding in half repeatedly. So there's many ways to make a non-standard unit of measure, and again, we do that all the time. So there's a few notes about that in the book, so check that out. Otherwise, it's about the imperial system and the metric system. So it's often called the English system. This is what's mostly used in the United States, but the rest of the world uses the metric system. I assume you're sort of familiar with these right here. You may have forgotten some of the individual things, like a lot of people forget how many feet are in a mile, but some people remember it. How many pounds in a ton or pints in a quart. So all of these are outlined in the book, and I'm very confident that you can read those, and that will refresh your memory on how each of these are connected. There's also temperature in the imperial units, and I'll get to that in a moment. The next unit in this section topic is the metric system. And so I'm going to spend a little bit more time on the metric system because I assume people aren't as familiar with it. And the only reason you're not familiar with it is just you don't use it often. So the point of this week is to use the metric system. So I've geared the activities toward using the metric system. So get out there and use it. We have length, the standard unit is a meter. Volume, the standard unit is a liter. Mass, the standard unit is a gram. And notice I have weight here, standard unit is a Newton. And comparing that back here, I didn't put mass over here because mass isn't really done much in the imperial system. There are units for mass that are different from weight. And so the kind of related thing to a pound is called a slug. And the difference between mass and weight is gravity. So for example, if something is 20 pounds on Earth and you take it to the moon, it will be lighter than 20 pounds because the moon's gravity is different. However, if it has a mass of 5 kilograms, it's going to be 5 kilograms on the Earth or the moon, that doesn't matter. A Newton takes into consideration the Earth's gravity. So a Newton is a measurement on Earth, not on the moon. But mass is constant whether it's on the Earth or the moon. So there is a difference between mass and weight, and that the connection there is gravity. So for example, with if I have some measurement in grams, and actually newtons are related to kilograms, so a newton is the force, oops, that's not a pen, it's the force of gravity, they usually call that little g, times whatever the kilogram measurement is. So if I wanted to find out my weight in newtons, then I would take the force of gravity as 9.8 meters per second, And if I multiply that by my mass in grams, which is about 72 kilograms, the product of these two things, kilogram meter per second, is what a Newton is. And that's like pounds. And that will vary if you're below sea level or above sea level slightly, and it'll certainly vary on the moon because it's a different gravitational system. Anyway, so besides the base units, sometimes it doesn't make sense to measure something in meters. So if I have like the width of a piece of paper or a note card, I'm probably going to use centimeters instead of meters. If I want to measure some medicine I need to take, I'm going to use maybe milliliters instead of liter. If I'm going to drink a Gatorade, I would measure that probably in liters, but I could use milliliters. So in any system, whether it's in the imperial system or in the metric system, there's usually an appropriate unit of measure for the size of the object. Like I'm going to go on a trip to Southern Oregon soon. I'm not going to measure my distance in feet or inches, right? I'm going to measure it in miles. So we choose a unit of measure based on what we're doing with it. So aside from the base unit, which is illustrated down here, we have, so again, base is either meter, liter, gram, the main ones we'll focus on. Then we have these prefixes we can attach to them, which adjust their size. And I have them listed here in order. And in this table, I have the prefix up on the top and then the meaning of it. So kilo literally means 1,000. So somebody says they weighed something and it came out to be 3 kilograms. Kilo, the K literally means 1,000, so that would be 3 times 1,000 grams. And I'm just replacing the K with 1,000 here because the K for kilo literally means 1,000. So 3 kilograms would be the same thing as 3,000 grams. So it's good to know those meanings because then you can do some conversions just by looking at it. Centi, for example, means 1/100th. So if I measured something and I found it to be 105 centimeters, and I wanted to get rid of the centi, I would just make a note that centi means 1/100th or 0.01, slang 1/100th read properly. So I could rewrite this as 105, replace the centi with 1/100th in either the decimal or the fraction form, whichever you like, and the meter is left behind. 100 goes into 105 1.05 times, so that means 105 centimeters is 1/500th meter, or slang 1.05. I would like you to the best of your ability, commit to memory that kilo is 1,000, hecto is 100, deca is 10. Then there's the base unit, which is either meter, liter, or gram. And then we have deci is a tenth, centi means 100th, and milli means 1,000th. There are other ones like computers. We talk about megabytes and gigabytes and terabytes. So I'm not going to get into those, however, here. I just want to stick with the basic ones for now that are our usual existence, physical reality, aside from computers. Another nice way to look at this table is in terms of how you can use it to make a conversion. So let's suppose we set the base unit to be meters, for example. So I make my base a meter. The table, in this case, I'm going from the largest to smallest. And I'm not skipping any unit. So these all move in powers of 10, right? So if I go back here, starting with milli, say 10 times a milli is a centi, 10 times a centi is a deci, 10 times a deci is the base unit, 10 times the base is a deca, 10 times a deca is a hecto, 10 times a hecto is a kilo. Okay, so they move up by powers of 10, just like our place value number system. So putting them in that order, starting with largest to smallest, this order tells me how to make a conversion. So if somebody says, hey, I've got a 1 meter, I need it to be in this measurement in millimeters. So I want to change 1 meter to some amount of millimeters. According to the table, I need to make a jump of 1, 2, 3 places in the table, and so the decimal that is imagined to be here has to move 3 times. So if I move it once, I'm going to need another 0, once again another 0, and once again, right? 1, 2, 3, 1, 2, 3. So 1 meter must be 1,000 millimeters. Okay, so this order can help me do conversions. If somebody said they measured something and it came out to 357.5 centimeters, and they wanted to convert that to, say, meters, then for that conversion here, I'm at centi, and I want to get over to meter. So let's see, switch the color back. So I want to know what this equals in meters. Then starting with centi, I want to move through the table 1, 2 times, but this time to the left. So the decimal would have to go 1, 2 to the left also. So this would be 3.575 meters. And you can move all the way across if you want to. So if you do know the order kilo, hecto, deca, base unit, deci, centimilli, you can't skip the base. That's an important one. These all modify it. And knowing the order largest to smallest means just moving through the table is just shifting the decimal in the same direction you moved on the table. Okay, so one more. Suppose somebody said they measured something to be 1.65 kilometers, and I want to rewrite that as some number of meters. I mean, we could even go totally nuts and say, how many centimeters is that, right? We could do that. So let's do the meter one first. To get the meters here, starting at kilos where I'm at, I would want to go 1, 2, 3 jumps to get to the meter place. So I went to the right, so the decimal would have to move to the right. So I would have the 1, the 6, the 5. So that's 1, 2 moves. I need to move one more time, so there have to be a 0 there. So 1.65 kilometers would be 1,650 meters. If we were dying to write that in centimeters, we just keep moving on the table 1, 2 more places on the table. And so we need 2 more zeros. So 1,650, 1, 2. So that would be 165,000 centimeters is 1.65 kilometers, if you ever needed to know that. So that's kind of a cute way of looking at the table and doing conversions. And there's some homework problems about that. All right, Fahrenheit versus Celsius, Celsius versus Fahrenheit. Celsius is the metric unit of temperature, and Fahrenheit is the imperial unit of temperature. Some people call it the English unit, but the English don't use it anymore, so I don't like to call it English. It's the imperial system back when, back from a long time ago. England probably hasn't used this in like 100 years. And I think we're the last country standing using things like Fahrenheit and feet. So just some, I would recommend memorizing these 4 facts: that water freezes at 32 degrees Fahrenheit, which is 0 degrees Celsius. Another good one is water boils at 212 degrees Fahrenheit, which is 100 degrees Celsius. In between here, average human body temperature is 98.6 or 37 degrees Fahrenheit. And room temperature, a lot of people say like, yeah, about 70 degrees is a comfortable room temperature. I like it cooler. Some people like it warmer, but 70 is approximately 21. I think it's 21.11111, but I'm just going to call it 21 here. These measurements here are pretty exact, and this one right here is an approximation because I left off a decimal here or a decimal there, whichever way you look at it. And then there's some formulas related to it. I'm not going to go over how to calculate these formulas. You can look them up when you need them or ask a computer to do a calculation. So if I were to plug in, say, 98.6 for Fahrenheit here and run through this calculation should spit out 37 Celsius. If I were to plug in a 21 Celsius into the Fahrenheit formula, it should spit out about 70 degrees when it does the calculation. So these are some good facts that you ought to know about temperature, Fahrenheit versus Celsius. And so again, water freezing, water boils, those are pretty straightforward, 0 and 100. Body temperature is 37 degrees Celsius, and room temperature would be about 21 degrees Celsius, let's say. Some people like it cooler like me, so I'd like it to be 20 degrees Celsius, but some people like it warmer, like 22 degrees Celsius. So that's that. Next. We're going to play around with some conversion fractions. And so if you know some fact about 2 units of measure, you can use that equality fact to make a conversion. So for example, I remember that there's about 2.54 centimeters in 1 inch, that a kilogram is about 2.2 pounds, and that a liter is just a little bigger than a quart. So 1 liter is 0.946 quarts. Let's see, did I write that correctly? No, I think I have that backwards. 1 quart is 0.946 liters. Yeah, that is backwards, because a liter is slightly bigger. And I'm going to look that up just to be safe. I think it goes this way. 0.946 liters is 1 quart. Let's go ask Google if my thing will work. Oh, here's the reading assignment, by the way. So again, read the book and then submit to me an outline that has the 5 main topics and a couple of bullet points for each of those topics about what was in there. So give me a couple of examples. All right, let's see. I want liter to quart. And hopefully Google will help me with this in my slow internet connection today. Usually it's a little snappy. So 1 liter is about 1.05. So if we switch that to go the other way, 1 quart would be 0.946 liters. Yeah, so I wrote it backwards the first time accidentally. Sorry about that. But I just remember a liter is slightly bigger than a quart. All right, back to my notebook here. So if I wanted to make some conversion, I can use these, and these are all kind of connections between, right? This is length in the metric system or the imperial system. This is weight / mass. We equate these, but they're not technically related directly because of gravity gets in the way, but we do it anyway. And this right here would be volume or liquid volume. So let's suppose that I measure something to be 3 feet 4 inches, and I want to know what that is in centimeters. So the first problem I have is that feet and inches together are trouble. So I think I want to convert everything to inches. So I would need another fact, like there are 12 inches in 1 foot, and I think most people know that. And if I wasn't sure how to use that 12, it would work like this. I have 3 feet right now, and what I'm going to do is I'm going to turn this equality into a fraction. So I'm going to write that as 3 over 1 and then multiply. To get rid of feet, it has to cancel with feet in the bottom, so that means inches would have to go in the top. There are 12 inches in 1 foot. So this tells me if I want to use this fact here to convert from feet to inches, I must multiply by that number. So the point of these conversion fractions is to answer the question, if you have a relationship like this, do you multiply by the conversion factor or do you divide? And every once in a while, most of the time I know, yeah, I should be multiplying here, I should be dividing. But every once in a while, I'm like, oh, what should I do? And this fraction sorts that out for you by the canceling of the units. So 3 times 12 is 36, oops, 36 inches, plus 4 is going to give me 40 inches. So this equals 40 inches. Now I'm going to use this next fact to get rid of inches to change to centimeters. So then I multiply by a fraction. I can write that over 1. Inches has to go on the bottom to match the inches in the top. They only cancel if they're in opposite positions. And then I can put centimeters in the top because I know inches and centimeters. The 2.54 is a centimeter to 1 inch. So this tells me if I want to get rid of inches and change to centimeters, I should multiply. So then whip out a calculator, and hopefully my calculator will work here. 2.54 times 40, and I get 101.6. And that's approximate 101.6 centimeters, which is almost a meter. So a meter is close to 40 inches. It's a little close to 39 inches. So that's using conversion fractions. So I'm just going to do one more example that's a little more complicated. I'm going to convert miles to miles per hour to feet per second. And this is always a striking fact that I think about. There's a lot more accidents these days because of cell phones, and whether it's a pedestrian looking at their phone and walking into a street, or it's somebody driving around texting or looking at their phone for some weird reason. So let's suppose you're cruising through a neighborhood at 30 miles per hour. So that literally means 30 miles divided by 1 hour, because per means divide. And I want to convert that into some number of feet per second. So that's my goal here, to reach that. So to make this happen, I need to change miles to feet, and I need to change hours to seconds. So then I need some facts to make that happen. So the facts that I'm going to have to apply here is that, let's see, miles and feet. I happen to remember that there are 5,280 feet in 1 mile. There are, 60 seconds in a minute, and 60 minutes in an hour. So I could use these two facts separately, or I could blend them together. So there's a couple approaches. I'm just going to use them separately for now. So to make this action happen, I rewrite my 30 miles as a fraction over 1 hour. And if it doesn't have a per unit like before, remember I just put 1 in the bottom and it was nameless, and that's okay. And then I want to start multiplying by fractions. So what do you want to get rid of first? I think since I wrote feet and miles first, I'll get rid of miles first. So the fraction has to have miles in the opposite position. So I can cancel miles, and I know a relationship between miles and feet. So there's the 5,280 to 1 mile. So this tells me, hey, if you want to convert from miles to feet, then you should be multiplying by this number. And if you can tell just by looking whether to multiply and divide, you don't need these fractions. But if you're ever in doubt, these fractions confirm what to do. And I can keep chaining them along. So I can just throw another one on here. I want hours to go. So that means hours has to go in the top of the next fraction. And hours I can change to minutes. So if I want to get rid of hours, I can change to minutes. And I know there's 60 minutes in 1 hour. So since it's in the denominator, the fraction bar means divide. Ultimately, I'm going to divide by 60. Now I have feet per minute. That's not what I want. I want feet per second. So I have one more fraction. Minutes has to go on the top to cancel. And seconds gets to go on the bottom finally. And there are 60 seconds in 1 minute. So to get rid of minutes and leave me with seconds, I have to put this together like that. So what's left? I have feet and I have seconds, and then otherwise I got a bunch of numbers to play with. So this tells me to start with 30, right? That's my first number, and then multiply by the 5,280 because it's in the top, and then divide by 60 because it's in the bottom. That wasn't a very good fraction bar. Divide by 60, and then divide by 60 again. So if I plug this into my calculator, I should get the conversion. So let's whip that out. So 30 times 5,280 divide by 60, and then again divide by 60 according to those conversion fractions. I get 44. So 30 miles per hour is the same, according to this calculation, as 44 feet per second. So if I'm driving down the road and I look at my phone, as I'm not doing 30 miles per hour, right? That's kind of fast, but not too fast. In a residential neighborhood, that's too fast probably. And I look at my phone for 3 seconds, right? What happened there? Multiply that by 3. Oh my gosh, 132 feet just went by. So I went by 2 or 3 houses in that time, if the houses are like 50 to 100 feet apart. Eek. So conversion fractions, fun stuff. There's an exciting application. Okay, last topic, precision. So when you measure something, regardless of the tool you use, there's some error, right? You lay something down. So let's, for example, suppose I had this red piece of paper, and I match it up with the big, oops, I wanted a line there. I match it up with the 0 centimeters, which would be about right here. And let's say it goes to about there. and that's the end of it. So then what I have to do is I kind of got to squint and look and say, oh, where does that line up there? It looks to be like 13, and it's a little more than a half. Let's see, how many lines are there? 1, 2, 3, 4, 5. Looks like there's 10 little lines in between. The big one is the fifth one. So what do you think? That's like 13.6 maybe? Could it be a little bigger than 13.6 or smaller? Yeah, but my eyes aren't good enough to see that. So I think I just drew a line that was 13.6 centimeters, but that 0.6 is like, yeah, I think it's 0.6. It's a little sketchy. So the idea is when you measure something with a tool like this, that final digit is almost never perfect. And so the general rule is that we just assume that it's within half of that smallest unit. So on this particular measure right here, I have those little lines in between the centimeters. So the smallest unit on the ruler here, smallest on ruler, would be 1/10 of a centimeter. And if I take half of that tenth, so divide that by 2 is what the rule says, that gives me 0.05 centimeters. So this measurement is really 13.6 plus or minus 0.05 centimeters. So there's a little margin of error with that. So that means, yeah, it's somewhere in between 13.55 centimeters to 13.65 centimeters. My eyes are, yeah, it's somewhere in that range. I'm just going to call it 13.6. If I were looking at my thermometer here, so I tried to use my meat thermometer here in the Metric Olympics. You'll see that video hopefully soon. It was not the best thermometer. I need to get a new one, and I feel like borrowing one from a friend or neighbor. So let's count the marks here. Like say from 100, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 of them to get from 100 to 50. So that's 50 units divided by 10 is 5. So each of those marks is worth 5 units. So the smallest measurement on the thermometer here, so thermometer would be 5 degrees Fahrenheit is the smallest line I can see on there. So anytime I measure something, I'm going to be off by up to half of that. So if I take that, divide it by 2, that gives me 2.5 degrees Fahrenheit. So if I look at this and I read and I say, yeah, that looks to me about like, okay, so right there, that looks to me at about, what would that be, 95-ish. So if that arrow is currently at, looks to me like 95 degrees Fahrenheit, in reality, there's some error in my looking at this and its ability to measure, and so it's really plus or minus 2.5 degrees Fahrenheit. So the, it's supposed to be an F, degrees Fahrenheit. So the actual measurement is somewhere between, subtract the 2.5, so 92.5, up to add the 2.5, 97.5 degrees Fahrenheit. So this is the rule of thumb here for precision on a measuring instrument. All right, so let's see if my internet's any faster. Read the book. Hope this was helpful for some of the homework. And then otherwise, the big things I wanted you to do this week are the Metric Olympic stuff, and I think this is just going to take forever to load. And I made a post about this, and I sent a video out about this earlier today. Do the Metric Me, do the scavenger hunt to get the equipment you can get, and then have fun doing the Metric Olympics. And so the video is of me and my cat doing the Metric Olympics. All right, that's it for me for now. Take care, stay in touch. Miss you guys. Bye-bye.